Trigonometry, Chapter 5, Trigonometric Identities, Section 4, More Identities, Video 3, Using Double Angle Identities, Part 2. This series is based on content from Pearson's Trigonometry 12th edition by Lial, Hornsby, Schneider, and Daniels. In the previous video, we used double angle identities to evaluate trig functions. In this video, we will use double angle identities to verify new identities. Now, it's worth mentioning that there's no way we can categorize all trig identities. Is there a finite number of them? I don't even know if that's the case. Probably, but it's somewhere in the thousands, if not a lot more. Anyway, let's verify this identity. The square of sine x plus cosine x is equal to sine of 2x plus 1. Which side should we start on? Well, let's start on the left side. And, well, if you square a binomial, you simply have to write it twice. Oh, by the way, there's no trig identity ready to do something, so let's do some algebra and write the binomial twice. Well, then we just have to multiply it out, FOIL, if you will. And if you carefully do that, pause the video if you need to, you should get sine squared of x plus 2 sine of x cosine of x plus cosine squared of x. So far we've just done algebra. Let's look for any identities we can capitalize on. The presence of squared trig functions suggests Pythagorean identities. In this case, we have a sine squared plus a cosine squared, and that's clearly equal to 1. So let's change the parts highlighted in yellow to just a plus 1 at the end, using a Pythagorean identity. And now we have 2 sine x cosine x plus 1. Now keeping in mind that our goal is, sine of 2x plus 1, observe the following. This expression, where we currently are, 2 sine x cosine x, is precisely the double angle identity for sine of 2x. So we can replace that with sine of 2x using a double angle identity, and we verified it. We were trying to show that the square of sine x plus cosine x is equal to sine of 2x plus 1. Mission accomplished. Not too bad. Now, could we have started on the right side with sine of 2x plus 1 and gone backwards? Maybe, but ask yourself this. If I had tried to reverse this process, started here, and used a double identity to turn it into that, would you have had the insight to be able to uncombine the 1 into sine squared plus cosine squared? It's technically a legal move, but unsimplifying something is not always the most easy thing to do, unless you've got a lot of experience. All right, so let's move on to the next identity. We got one more we're going to do in this video. We're going to verify that sine of 4x equals 4 sine x cosine cubed x minus 4 sine cubed x cosine x. That's a mouthful. Now, normally one of the strategies we use is to pick the more complicated side and try to turn it into the simpler side. But in this case, we're going to start with sine of 4x, and we're going to use a double angle identity on the left side. To do this, we need to view 4x as twice an angle, and in this case, sine of 4x can be viewed as sine of 2 times 2x. And in general, any even number can be viewed as twice a whole number. So if we use sine of 4x, we're going to rewrite as sine of 2 times 2x. That's just algebra. But now we're going to use the sine double angle formula. We're going to apply sine of 2 theta equals 2 sine theta cosine theta. But in this problem, the theta is being replaced by the 2x. So everywhere there's a theta in our identity, we're going to replace it with the 2x. And when we do that, it ends up looking like this. 2 sine of 2x cosine of 2x, thanks to a double angle identity. But now we have both sine of 2x and cosine of 2x, which screams use double angle identities again. Now, sine of 2x has one identity, but cosine of 2x has 3 to choose from. So let's start by rewriting sine of 2x first. Sine of 2x is 2 sine x cosine x. Don't forget the 2 that was in front. But what about the cosine of 2x? Which identity do we use? When you're making a decision like this when verifying identity, focus on the goal. That'll often give you some insight. The goal is highlighted in yellow right now. Notice each of the two terms in our goal has a coefficient of 4. Well, at its current state, the identity is ready to produce those 4s because of the 2 times 2 in the front. So whatever goes here shouldn't change that. We have the 4s. We don't want any extra coefficients. The only cosine 2x identity that won't change the coefficients is this one, cosine squared x minus sine squared x. Making these moves sometimes requires a little finesse and a little observation, but usually a lot of experience and exposure to this type of problem. At this point, we're practically home free because all that's left now is to distribute this across the subtraction. We would get 4 sine cosine cubed x and 4 sine cubed x cosine x, which is exactly what we wanted. The identity has been verified. Now you try. Pause the video and try to work the following. Verify the identity. 2 cosecant of 2x equals tangent x plus cotangent x. This first part of the answer wasn't supposed to be there, but pause the video and give it a try. If you haven't paused the video yet, here's your warning. Here comes the solution. Now, unlike most videos, I'm going to walk through the solution because it's kind of a lengthy one. All right, so since we don't have a double angle, we're going to start on the left side. Since we don't have a double angle identity for cosecant of 2x, we're going to express it in terms of its reciprocal. So 2 cosecant of 2x is 2 over sine of 2x. We have a double angle identity for sine of 2x. We get 2 over 2 sine x cosine x. Clearly, we can cancel the 2's and reciprocate the sine x and cosine x to get cosecant x secant x. Well, that's nice, except it's not our goal. This is an example of an identity where sometimes the better strategy is to work both sides down to a common middle ground. Since there's really not much we can do with cosecant x secant x besides reciprocate it back, we're going to pause the left side and we're going to focus on the right side and see what happens. So let's start with tangent of x plus cotangent of x, and let's use the strategy where we turn everything into sines and cosines. Tangent is sine x over cosine x. Cotangent is cosine x over sine x. Well, now we're just adding fractions, which means common denominator. Common denominator would be sine x cosine x. So give this first fraction a sine on top and on bottom. That would create sine squared on top. Give the second fraction cosine x on top and bottom. That would create cosine squared on top. The common denominator would be sine x cosine x, and the numerator would be sine squared plus cosine squared. If you need to write down those steps individually, I understand. But wait a minute, the numerator is now just 1. And now it's 1 over sine x cosine x, which reciprocates into cosecant x secant x. Done. Since both 2 cosecant 2x and tangent plus cotangent, let's try that again. Since both 2 cosecant 2x and tangent x plus cotangent x equal the same thing, they both equal cosecant x secant x. They must also equal each other, and this verifies the identity.